Good morning, I am Aditi studying in BSc Chemistry Honours, second year. Today in this video, we are reading electromagnetic spectrum, absorption spectra, in other words, infrared spectroscopy. Introduction. All compounds containing covalent bonds, whether organic or inorganic, absorb in the infrared IR region of the electromagnetic spectrum, and a contrast to a UV spectrum which contains only a few bands. An IR spectrum contains a number of peaks which provide a wealth of information about the structure of the compound. Therefore, IR is by far the most widely used spectroscopic technique for determining the functional groups present in an organic compound. Units of IR radiations. The position of absorption in the IR region can be expressed either in terms of wavelength in micrometers or in terms of wave numbers, number of wave per centimeter. Thus, where V is the frequency in hertz. However, most chemists prefer to use wave number rather than wavelengths as units since the energy of radiations is directly proportional to the wave number. Higher the wave number, higher the energy. Parts of IR region. The IR region of the electromagnetic spectrum extends from 0.8 to 200 nanometer. For convenience, it has been divided into three parts. The region which extends from 0.8 to 2.5 nanometer is called the near infrared region. That which extends from 2.5 to 15 nanometer is called the ordinary infrared region, and that which extends from 15 to 200 nanometer is called far infrared region. The near infrared region corresponds to energies in the range 11.44 to 55.75 mole inverse, while the far infrared region corresponds to the energies in the range of 0.14 to 1.9 mole inverse. Since there are only a few absorptions of organic molecules in these regions, they are seldom used for spectroscopic purposes. The radiations in the commonly encountered in the vibrational states of organic compounds, consequently almost all the organic compounds show a number of absorptions in this region, and hence this region is extremely useful to an organic chemist. Principle of IR spectroscopy. The absorption in the infrared region occurs due to the excitation of molecule from the lower to the higher vibrational level. Since each vibrational level is associated with a number of closely packed space rotational levels, IR spectra may be regarded as vibrational rotational spectra. We know that the atoms in a molecule are not readily helped but keep on vibrating to and fro about an average internuclear distance. Thus, each bond has a characteristic or native stretching and bending frequency at room temperature. Most of the molecules of a sample will be in the lowest vibrational level. However, when ordinary infrared radiations are passed through the sample, some of the molecules will absorb a quantum of infrared radiation of appropriate energy and thus get excited from the lowest to the next higher vibrational level. In this higher vibrational level, the native frequency of the bond remains to be the same, but its amplitude increases. Due to this increased amplitude, an oscillating dipole will be set up in the molecule. The interaction of this oscillating dipole movement with the electric vector of the infrared radiation leads to absorption of energy. When the excited molecule reverts to the original ground state, the absorbed energy is released as heat. Since the absorption in the IR region, like in the other region, is quantized, therefore only a selected frequency of the incident IR radiation will be absorbed. As a result, each molecule will show a fixed number of peaks in the IR region. It may be noted that all the bonds in molecule are not capable of absorbing infrared energy even if the frequency of the incident radiation exactly matches the native frequency of the bond. Only those bonds which are accompanied by a change in dipole moment will observe in the infrared region. Such vibrational transitions which are accompanied by a change in the dipole moment of the molecule are called infrared active transitions and hence are responsible for absorption of energy in the infrared region. Conversely, those vibrational transitions which are not accompanied by a change in dipole movement of the molecule are not directly observed and are said to be infrared inactive transitions. For example, vibrational transitions bonds are accompanied by a change in dipole moment and hence observed strongly in the infrared region. On the other hand, carbon-carbon double bond of symmetric alkanes and of symmetric alkynes are not accompanied by any change in the dipole moment and hence do not absorb in the infrared region. Molecular vibrations, types of fundamental vibrations. We have stated above that the atoms in a molecule are not rigidly held. These may be compared to a system of balls of different sizes connected to springs of varying strengths. Here balls correspond to atoms and springs to chemical bonds. Just as we can compress and extend or bend a spring, in a similar way, bonds can be stretched or bent. As a result, there are two types of fundamental vibrations for molecules: stretching and bending. In stretching vibrations, the distance between the atoms increases or decreases, but the atoms remains in the same bond axis. On the other hand, in bending vibration, the positions of the atoms change with respect to the original bond axis. These two types of vibrations are shown in figure 11.16 for an AX2 system such as NH2, CH2, NO2, etc. We know that more energy is required to stretch than the bend a spring, that stretching vibrations requires more energy than bending vibrations. That of a bond will appear at higher energy if there is higher wave number in the vibration of the same bond. Bending vibrations are also called deform. The absorption of energy in the higher region is a quantized process. Therefore, it will be occur at certain quantized frequencies. In nutshell, absorption of ordinary infrared radiation corresponding and this amount of energy is sufficient to bring bending vibrational frequencies of covalent bonds in most of the origin. Types of stretching vibrations. There are following two types of stretching vibrations. Symmetric stretching. A stretching vibration is said to simultaneously stretch or correspond compressed. It is denoted by stretching vibration of a CH2 group absorbed at 2853 centimeter. Asymmetric or antisymmetric stretching. A stretching vibration bond is being stretched while the other is being compressed. Example, the antisymmetric stretching vibration of a CH2 group absorbed. In general, antisymmetric vibrations require higher energy than at higher wave number or higher frequency or lower wavelength. Types of bending vibrations or deformation. These are of two types: out of plane bending vibrations and in plane bending vibrations. In plane bending vibration, in these vibrations, molecules, these are of following two types. In plane seizing deformation, in this bending mode, the blades of a scissor, for example, the plane in scissor, absorb at about 1465 centimeter. In plane rocking deformation, in this bending mode, the one side and the other side, for example, in plane rocking, around 700 to 20 centimeter. Out of plane bending deformation. In this vibration mode, the two atoms move out of the plane of the molecule. These are of the following two types. Out of plane wagging deformation. In this bending mode, both the atoms simultaneously move above and below the plane of the molecule with respect to the central atom. The wagging deformation of a CH2 group absorbs at about 1250 centimeter. Out of plane twisting deformation. In this type of bending vibration, one atom moves above and the other below the plane of the molecule with respect to the central atom. For example, the out of plane twisting vibration of a CH2 group like wagging vibration absorbs around 1250 centimeter. All the four types of bending vibrations are shown in figure 11.18. Scissoring, rocking, wagging and twisting. Look at these figures. Similarly, other AX2 groups such as NH2, NO2, etc. behave similarly, hence Plus and negative sign imply vibrations above and below the plane of the paper. Calculation of vibrational frequencies or wave numbers, Hooke's law. The frequency of the stretching vibration of any bond can be calculated fairly accurately by the application of the Hooke's law, where m1 and m2 are the masses of atoms in grams and is called the reduced mass. V is the frequency, is the wave number of the stretching vibration, C is the velocity of light, and K is the force constant and is related to the strength of the bond. The values of K for single, double, and triple bonds are about approx 5, 10, and 15 to 10 raised 9 centimeter respectively. In the SI units, the value of K for single, double, and triple bond are approx 500 nanometer inverse, 1000 nanometer inverse, Newton meter inverse. If m1 and m2 are the atomic masses of the atoms forming the bond and 6.02 raised to 10 ki power raised to 23 is the Avogadro number, then position and intensity of IR absorption bands. Position of absorption bands. From the equation of Hooke's law, it is evident that the frequency of absorption of a stretching vibration depends upon the following two factors: strength of the bond or the force constant of a bond, masses of the atoms forming the bond or the reduced mass of the system. The third factor which affects the absorption frequency is the type of molecular vibration. Let us know discuss these three factors one by one. Strength of the bond. Stronger the bond, higher is the stretching vibrational frequency. We know that the strength of the bond increases in the order single bond, double bond, triple bond. Therefore, triple bond stretching vibrations, etc., absorb at a higher frequency or wave number than double bond stretching vibrations, etc., which in turn absorb at a higher frequency than single bond stretching vibrations. Masses of the atoms. The lower the masses of atoms forming the single bond or lower the reduced mass of the system, higher is the stretching frequency. The effect is particularly marked when one of the two atoms forming the single bond is a very small proton, which generally absorb in the region 3700 to 2630 cm. For example, OH bond absorbs near 3570 cm and the OD bond absorbs around 2630 cm. Here the strength of the bonds are nearly the same, but the mass of one atom is double than that of the other. It may be noted that in order to predict extent trends, it is essential to consider both the force constant and the masses of the atoms together. In some cases, if the predictions are made on the basis of masses of the compounds show a number of absorptions in the region, and hence this region is extremely useful to an organic chemist. Atom alone, we are able to commit mistakes. For example, on the basis of masses of atoms alone, we would expect that the stretching frequency should decrease in the order, but in actual practice they increase. The reason being that the force constant increases in the order. Thus, HF bond observes around 4138 cm, OH around 3570 cm, NH around 3300 cm, and CH around 3000 cm. Types of molecular vibration. The frequency of an IR absorption band depends upon the type of the molecular vibration, whether stretching or bending. We have already discussed about the stretching vibration of a group requires more energy and hence appears at a higher frequency or the wave number than the bending vibration of the same group. Further, among stretching vibrations, asymmetric stretching vibration absorb at a higher frequency than the corresponding symmetric stretching vibration. For example, asymmetric stretching of a CH2 group absorbs at 2962 cm, while symmetric stretching vibration absorbs at 2853 cm. Similarly, different bending vibrations of a CH2 group absorbs at different frequencies or wave numbers, ceasing at 1465 cm. wagging and twisting around 1050 centimeter, while rocking vibration absorbs at about 720 centimeter. Intensity of absorption bands. The differently peaks in an IR spectrum have very different intensities. The two factors which control the absorption intensity are concentration of the sample. In general, greater the number of the molecules in the sample and more the number of absorbing groups in a molecule. More intense is the spectrum, thus, a more concentrated sample gives a stronger spectrum than a less concentrated one, other things being equal. Similarly, a molecule such as nonene, which is rich in CH bonds, has a stronger absorption for a CH stretching vibration than a molecule of similar size with relatively few CH bonds. Magnitude of dipole moment change. For a given amount of the sample, the most important factor which governs the absorption intensity is the dipole moment change. Higher the dipole moment change, stronger is the absorption. To illustrate this point, let us compare the C double bond C stretching vibration of 2-methylpropene and 2,3-dimethyl 1,2-butene. Because of the electron donating effect of the two methyl groups, isobutylene has a dipole moment along the C double bond C. When this bond undergoes stretching, the dipole moment increases because the dipole moment is the product of both charge and distance. As a result of this changing dipole moment, the C double bond C stretching vibration in isobutylene is infrared active and absorbs at 1640 cm. On the other hand, the alkylene 2,3-dimethyl 2-butene has no dipole moment, and stretching the double bond also does not impact any dipole moment change. In other words, the molecule end is stretched form have the same dipole moment 0, and hence C double bond C stretching vibration of this alkane is infrared inactive and hence does not show any absorption in the region 1600 to 1700 centimeter. Further, the intensity of an IR's absorption peak depends upon the size of the dipole moment associated with the vibration. Thus, 3,4-dimethyl 3-butane has a very little dipole moment. Propyl groups differ very little in their electronegativities. Further, as a result of C double bond C structure and dipole moment, it's so small that for all practical purposes, this vibration does not share absorption in the IR spectrum. For further illustration, let us consider the intensity of C double bond C and C double bond C stretching. Carbonyl group has a much higher dipole moment than C double bond C double bond, therefore produces a much higher dipole moment change than a C double bond C stretching. As a result, the stretching is much higher than that of the C double bond C stretching. Number of fundamental absorption bands. We have discussed above that absorption in the infrared region occurs due to the different vibrational levels. Therefore, it is logical to expect that the number of fundamental which a molecule might show in its IR spectrum must be equal to the number of fundamental modes possible. Let us now calculate the total number of vibrational modes. Non-linear molecules. A non-linear molecules having n atoms has 3 n degrees of there are translation along the three axes x, y, z. There are rotational. The molecule has 3 and 6 fundamental vibrational modes and hence should show 3 and 6 fundamental bands. Thus, a non-linear molecule such as benzene should show absorption bands. Linear molecules. In case of linear molecules, there are only 2 rotational degrees is due to the reason that rotation about its own axis does not bring about any change. Atoms but rotation about the other 2 axes does. Therefore, for linear molecules, there are modes possible and hence a linear molecule should show 3 and 5 absorption band indents. For a linear molecule such as CO2, the number of fundamental bands should be. However, in practice, it has been observed that the predicted number of bands are in the infrared spectrum of any given molecule. It is because of the following reasons. The necessary and the sufficient condition for a fundamental vibration to appear spectrum is that it must cause a change in the dipole movement of the molecule. Thus, molecule certain symmetry elements will show lesser number of absorption bands. For example, vibration of ethylene and the symmetrical stretching of the 4 CH bonds of methane. Absorption band in the IR spectrum. Fundamental vibration which are too weak to be observed as bands. Fundamental vibration which fall outside the region being examined. Fundamental vibrations that are so close that they overlap. Beside these fundamental bands, they may appear some additional non-fundamental are of three types. Overtones, these appear at twice, three times the wave number of frequency vibration but are about 10 to 100 times less intense than the fundamental vibrations. Wave number of a fundamental vibration, then weak first and second overtone band will appear at wave numbers and correspond transitions. Aromatic compounds show many weak overtone and combination bands discussed below. In the regions 1667 to 2000 cm, the relative shapes and number of three peaks can be used to tell whether an aromatic compound is mono, di, tri, tetra, penta, or hexa substituted. These overtone bands can also be used to distinguish positional isomers such as ortho, meta, and para substituted benzene. Combination bands. These appears at some of the wave numbers of the two fundamental vibrations. It may however be noted that not all possible combinations occur. Difference bands. These appears at wave numbers which correspond to difference in wave numbers of two fundamental vibrations. It may be noted that these non-fundamental vibrations are 10 to 100 times less intense than the corresponding fundamental vibrations. Due to combination of all these reasons, the IR spectrum of an organic compound is usually very complex. Fermi resonance. If the energy of a fundamental vibration lies close to that of an overtone or combination band, the transfer of energy occurs from the fundamental vibration to the overtone vibration. As a result, intensity of the overtone or the combination band increases. This mechanical coupling between fundamental and overtone or combination band is called Fermi resonance and is often observed in the IR spectra of carbonyl compounds. For example, carbonyl group of cyclopentanone shows two peaks in the carbonyl group region. This is due to Fermi resonance between fundamental vibration of the C double bond group and first overtone of the fundamental vibration of the alpha methylene group. Selection rules. Most of the organic molecules possess dipole moments due to the presence of polar covalent bonds linking the constituent atom. When a polar covalent bond undergoes a stretching vibration along the internuclear axis, or two polar covalent bonds sharing a common atom undergo a bending vibration, and oscillating or fluctuating dipole moment is produced. Interaction between this oscillating dipole movement and the electric vector of the infrared radiation leads to the absorption of energy from the radiation. This interaction and hence absorption of radiation can occur only if the dipole moment at any extreme of the vibration is different from the dipole moment and the other extreme of the vibration. However, in the Raman effect, absorption of energy occurs due to interaction between the radiation and polarizability of the molecule. Thus, there are different rules called the selection rules which determine whether a particular vibration would be infrared active or Raman active. In general, vibrations which are centrosymmetric about the center of symmetry of the molecule are active in the Raman and inactive in the infrared, while those react in transitions which are not centrosymmetric are inactive in the Raman but usually active in the infrared. This means that the Raman and the infrared spectra are complementary. However, the IR spectra are more easily obtained and are also most informative for organic chemists since most of the functional groups are not centrosymmetric. To illustrate the concept of the centrosymmetric vibration, let us consider CO2 molecule. Since the molecule is linear, it has 395 for fundamental vibration. These are shown below. Symmetrical stretching, asymmetric stretching, bending vibration. The symmetrical stretching vibration is centrosymmetric. It is not accompanied by any change in the dipole movement of the molecule and hence is IR inactive but in Raman active and appears around 1340 cm in the Raman spectrum. The bending vibrations C and D are identical but they occur in perpendicular planes. Such vibrations which require same amount of energy and hence absorb at the same frequency or thus wave number are called degenerate. In CO2, such vibrations absorb at 667 cm. Thus IR spectrum of CO2 molecule shows only two fundamental vibrations 2352 667 cm instead of 4 as predicted by the formula 3n 5. Factors affecting vibrational frequencies. We have discussed about the approximate frequency of absorption of any bond in its IR spectrum can be calculated by the application of the Hooke's law. But it has been observed that the experimental value of the absorption frequency of a particular bond is seldom equal to its calculated value. This arises due to the following factors: vibrational coupling, hydrogen bonding, electronic effects. Let us now briefly discuss these factors. Vibrational coupling. An isolated CH bond has only one stretching frequency. However, if two such CH bonds share a common carbon atom, such as in a CH2 group, then the two CH stretching vibrations interact mechanically to give rise to two coupled vibrations, each one of which occurs at a frequency different from that of its isolated CH bond. They are called symmetric and asymmetric stretching vibrations and are shown in figure 11.18. The asymmetric stretching vibrations occurs at a higher wave number than the symmetric CH stretching vibration which occurs at 2853 cm. Similarly, wave number than the symmetric vibration which absorbs at 2872 cm. Hydrogen bonding. Hydrogen bonding causes significant downward shift in the absorption frequencies of OH and NH bands of alcohols, phenols, carboxylic acids, and amines. This may be explained as follows. The molecule of H bonded alcohol may be represented as follows. Look at this. Due to H bonding, the length of the OH bond increases. In other words, the OH bond weakens and hence the force constant decreases, which shifts the absorption frequency to lower wave numbers. Further, the associated OH stretching absorption band is broad since the OH groups are associated in aggregates of various sizes, dimers, trimers, tetramers, etc., and shapes, giving rise to a variety of different kinds of hydrogen bonds, and therefore a spectrum of closely spaced OH absorption frequencies result, giving it the appearance of broad band. Some important generalizations about the effect of H bonding on the IR absorption spectra are as follows. The stronger the H bond, greater in the downward shift in the absorption frequency. Intramolecular H bonding gives broader bands, while intramolecular H bonding gives sharp and well-defined bands. The intensity of intermolecular H bonding absorption bands are concentration dependent and decreases with dilution. In contrast, the intensity of intramolecular H bonding absorption bands are concentration independent. Concentration has no effect on the intensity of intramolecular H bonding because it takes place within the same molecule. The downward shift is more pronounced in intermolecular H bonding than in intramolecular H bonding. Let us now illustrate the above generalization with the following examples. Alcohols and phenols. The free OH group of alcohols and phenols absorbs in the region 3650 to 3600 cm, but intermolecular H bonded OH groups gives broad bands in the region 3400 to 3200 cm. Sharp free hydroxyl groups are usually seen but only in the vapor phase or in dilute solutions in non-polar solvents such as CCl4, etc. For example, 1-butanol in 1% solution in CCl4 shows a sharp band and 3650 cm due to OH stretching of the free OH group and a broad absorption band around 3350 cm due to hydrogen bonded. OH group, thus there is a significant downward shift of about 3650 to 3350. H bonding, however, in case of intramolecular H bonding, this downward shift is small. Solution of ethylene glycol in CCl4 shows two bands at 3644 cm to and 3612 cm. To the OH stretching frequency of unbonded or free hydroxyl group, whereas the intramolecularly H bonded hydroxyl group. Thus, there is a downward shift of only 3644 cm to intramolecular H bonded hydroxyl group. Further, in the IR spectrum of ethylene glycol, the band at 3612 cm is merged, thereby showing that most of the molecules of ethylene glycol exist in the steric and dipolar repulsions of the hydroxyl groups. This shows the instability due to repulsions is more than compensated by stability gained through H bonding. Carboxylic acids. A carboxylic acid exists in monomeric form in very dilute 1760 due to free C double bond O stretching vibration. However, in concentrated solution exists in the dimeric form. In the cyclic dimeric structure, the H bonds are quite stronger and hence OH bond appears at lower wave numbers as compared to the absorption frequencies at around 3600 cm. Similarly, the C double bond O stretching vibration of carboxylic acid appears as compared to the free C double bond O stretching vibration which absorbs around amines. Since nitrogen is less electronegative than oxygen, therefore H weaker than those in alcohols. As a result, downward shifts in frequency of absorption are lower than those absorbed in alcohols. For example, an N stretching of free 3500 cm, but absorption due to H bonded amines appears around 3300 cm. Electronic effects. The electronic effects such as inductive effect, resonance gratefully affect the C double bond O, C double bond C stretching vibrational frequencies. The effects cannot another and hence always work together. In some cases, the inductive effect overweights, while in other reverse is true. The overall effect of these electronic effects is to increase constant of the C double bond O, and accordingly the absorption shift to higher or lower discussed below. The following are some of the important generalizations. Inductive effect. As the number of electron donating alkyl group increases bond, the bond length increases or the force constant decreases and the hence absorption wave numbers, for example. Introduction of an electron withdrawing group increases the force constant because of the I effect and hence the absorption shifts to higher wave numbers. For example, look at these examples. Acetone, chloroacetone, alpha dash, and dichloroacetone. Resonance effects. Conjugation lowers the force constant and hence decreases the frequency of the C double bond stretching and C double bond C stretching, regardless of the fact whether the unsaturation is brought about by a double bond or an aromatic ring. In general, conjugation lowers the absorption frequency by about 2545 cm. For example, methyl vinyl ketone, benzaldehyde, acetophenone. All the three factors discussed above operate together, and the actual frequency of absorption of any functional group depends upon their combined effect. On the basis of combined effect of H bonding, inductive and resonance effect, we can easily explain that absorption frequencies of aliphatic aldehydes, ketones, carboxyl acids, and their functional derivative decrease in the order. Measurement of or recording of IR spectra. The model double beam infrared spectrometer consists of 5 main parts: radiation sources, monochromator, grating, detector, amplifier, and a recorder. The flow sheet diagram of a double beam IR spectrometer is shown in figure 11.19. Look at this figure. Radiation source. The most common source of infrared radiations is the nearest glower, which offloads sintered mixture of the oxides of zirconium, uranium, albium. The rod is electrode heated to 1773 Kelvin to produce infrared radiations. Alternatively, a rod of silicon carbide also be electrically heated to produce infrared radiations. Monochromator. To obtain monochromatic radiations, optical prisms or gratings are used. Gratings give better resolution at high frequency than do prisms. Cell containers. The most commonly used material for the cell containers of the prism is NaCl, transparent to infrared radiations down to 625 cm. Certain metal halides such as CSI or a mixture THI can also be used, but glass or quartz cannot be used since it absorbs most of the infrared radiation. Disadvantage of using NaCl is that it is hygroscopic and hence it must be protected from moisture, generally down by heating them about 20 Kelvin above the room temperature. Detectors. Most of the modern instruments use thermophile detector. These work on the thermometer principle that if two different metal wires are joined here to tail, then a difference in temperature between and tail causes a current to flow in the wires. In the infrared spectrometer, the current produced proportional to the intensity of radiation falling on the thermopile. The radiation from the source are in two beams. One of the beam that passes through the sample under examination is called the beam and the reference beam. Presentation of data. Due to absorption of certain frequencies by the sample, the intensity of the transmitted sample decreases while that of the reference beam remains to be the same. The detector then determines the range, the intensity of the two beams and plots a graph between transmittance along y-axis and wavelength or along x-axis. This graph is called IR spectrum. For example, illustration IR spectrum of the figure shown 11.20. As is evident in many parts of the spectrum, the transmittance is nearly 100%, meaning that the is nearly transparent, does not absorb the radiation of that frequency. The maximum absorption is represented as a minimum on the chart. Even so, the absorption is generally called a peak. Unlike in UV spectral, the intensity of band in the IR spectra cannot be easily determined with what for an organic chemist it is sufficient to know that the bands are strong, medium, weak, of variable intensity, are or broad or sharp. Sampling techniques. An infrared spectrum can be scanned by using the sample in the gaseous, liquid, solid, or in the solution phase. However, solid are not used as such since they scatter radiations too much. Therefore, they are either dissolved in CCl4, CH2, CHCl3, etc., or ground with liquid paraffin to form neutral melts or converted into KBr plates with powdered KBr and compressing the whole into a transparent pair by applying about 2000 IB pressure. In whatever form the sample is used, only a small amount, 10 to 15 of the sample is required to scan an IR spectrum, but the sample must be perfectly dry since water absorbs strongly at 3710 cm due to OH and 1630 cm due to OH bending. These absorptions may overlap with the absorption bands due to the sample under examination. Parts of IR spectrum. For sake of interpretation, the IR spectrum of any organic compound may be divided into two parts: functional group region, fingerprint region. Functional group region, the portion of the IR spectrum extended from 4000 to 1400 cm is called the functional group region because almost all the functional groups absorb in this region. This portion of the spectrum mostly contains absorption bands due to the stretching vibrations. Fingerprint region, the portion of the IR spectrum extended from 1400 to 900 cm is called the fingerprint region. This portion contains many absorptions due to bending vibration as well as absorptions caused by stretching vibrations of C, 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 CO and CN bonds. Since there are many more bending vibrations of the molecule than stretching vibration, the region 1400 to 900 cm of the spectrum is particularly rich in absorption bands and shoulders. Most of these absorption bands cannot be analyzed completely, but a peak by peak response in the infrared spectra of two different samples in an excellent criteria of identity. That is why this region is called the fingerprint region. Compounds having the same functional group shown differences in the fingerprint region. In a nutshell, we can safely say that the identity of IR spectra of two compounds is much more characteristic than comparison of their many physical properties. Limitations: IR spectra cannot be used to distinguish enantimeters since enantimeters have the same spectra. It is also not possible to distinguish a straight chain alkane containing 30 carbon atoms from that containing 29 or 31 carbon atoms by comparing their IR spectra. Such a distinction can, however, be made on the basis of their mass spectra. Characteristic absorption of various functional groups. In order to identify the functional group present in an unknown organic compound from its IR spectrum, we must know the frequencies or the wavelengths at which the various functional groups absorb. To this correlation tablets have been prepared which list the approximate ranges of frequencies within which a particular functional groups absorb. With the help of these correlation tablets, we can determine with functional groups are present in an organic compound. The characteristic absorption frequencies of various functional groups are given in table 11 point. You can look at this on this table. Special features of some classes of compounds. We have listed the approximate range of characteristic IR frequencies of various functional groups. Let us now discuss the spectral features of some classes of organic compounds in little more detail. Hydrocarbons, alkanes. The IR spectra of alkanes are generally quiet since they do not contain any functional group. They show only the three types of vibrations: CH stretching, CH bending, and CH stretching vibration as shown in figure 11.11. Some important absorption bands of alkanes. Look at this figure. Alkenes. IR spectra of alkenes show many characteristic absorption bands which are very useful for structure determination. The most important band is very vinylic stretching which absorbs slightly above 3000 cm, usually in the range 3010 to 3100 cm. The actual position, however, depends upon the extent of substitution. The C double bond C stretching vibrations give rise to bands of vibration variable intensity in the region 1660 to 1620 cm. The conjugation usually shift this band to lower frequency which increase intensity. The reason being that the conjugation decreases the double bond character due to resonance as a result. The force constant decreases and hence the frequency of absorption also decreases further due to resonance. The probability of excitation increases and hence the intensity of the band increases accordingly. The C double bond C frequency increases as alkyl groups are attached to the double bond. For example, simple mono substituted alkenes absorb around 1640 cm. 1 di substitute 1 alkenes absorb at about 100 650, while tri and tetra substituted alkenes absorb near 1670. In general, unsymmetrical substituted transition absorbs at higher frequency. Group has a rather weak intensity, certainly much weaker than C double bond O group in many cases symmetrical D substituted alkenes. The reason being that in such cases there is no significant dipole moment during the vibration. Absorptions arising from CH bending vibrations appear in the region 1650 cm. Location of these bands can often be used to determine the substitution pattern of the double bond configuration. Monosubstituted alkenes give two strong bands in the region 920 to 905 cm. Desubstituted alkenes for the type R2CH2 give a strong bond. Look at the figure 11.12. Some important absorption bands of alkenes. Look at this figure. Alkynes. Terminal alkynes show three absorption bands. The two strong band appears up around 630 cm due to stretching and bending vibration respectively. The third band is of medium intensity and usually appear in the region 2140 to 2100 cm due to C triple bond C stretching. Some important absorption bands of alkynes. Look at this table. Aromatic compounds. Aromatic compounds show three types of vibrations. C stretching in the region, C double bond stretching in the region. Actually, there are four such bands which appears at 1600, 1580, 1500, 1450. Absence of these bands indicate that the compound is not aromatic. CH bending vibration which appears in the region 900 to 690 cm. These bands are quite useful in determining the substitution pattern. If the band near 690 cm is absent, it cannot be a mono-substituted benzene. Beside these, several weak overtones and combination bands appear in the region 2167 cm. These can also be used to identify the ring substitution pattern. Table 11.14 characteristic IR absorption frequencies of aromatic hydrocarbons. Look at this table. For illustration, IR spectra of toluene in given in figure 11.21. Look at this figure 11.21. Alcohols and phenol. The IR spectra of alcohols and phenol show two characteristic bands due to OH bond and vibration in the region. Look at the figure characteristic IR absorption frequencies of alcohols and phenol. Effect of H bonding on the position of absorption of OH stretching vibration of an alcohol is determined as a pure neat liquid film, a broad OH stretching vibration due to intermolecular H bonded OH group as the alcohol non-polar solvent such as CCl4. A sharp peak appears to the left of the broad band OH stretching vibration. When the solution is further diluted, the broad intermolecular almost vanishes and instead a sharp bend due to the free OH vibration appears. Look at this figure 11.22. Like intermolecular H bonding also weakens the OH bond, the OH stretching band to lower frequency. For example, the OH band is centered around. Table 11.17 C double bond O stretching frequencies of some ketones. For illustration, IR spectrum of 2-hexanone is shown in figure 11.25. Carboxylic acids. The IR spectra of carboxylic acid show the following three characteristic absorption bands. In concentrated solution, carboxylic acid shows an extremely broad OH stretching absorption band in the region 3400 2500 cm. This band is attributed to the strong H bonding present in the diametric structure of carboxylic acids. However, in very dilute solutions, several weak bands appear in the region 2700 to 2500 cm due to H bonded OH group, since the H bonded OH stretching band of alcohols occurs in the region 3400 to 3200 cm as compared to those of carboxylic acids in the region 3400 to 2500 cm. Therefore, carboxylic acids form stronger H bonds than alcohols. Aliphatic saturated carboxylic acids shows a strong band in the region 1700 to 5 to 7700 cm. Due to C double bond O stretching vibration, conjugation with the C double bond C or aryl group usually shifts this absorption band to lower frequency. In contrast, halogenation at the alpha carbon leads to an increased frequency. The CO stretching vibration for acids appears as a medium intensity. Carboxylic acids also show the OH bending vibration, the in plane near 1460 cm, while the out of plane bending vibration appears as a broad band, are usually of low to medium intensity. For illustration, IR spectrum of propanoic acid is shown in figure 11.26. Carboxylic acids and their derivatives. The IR spectra of carboxylic acid derivatives, acid chlorides, shows acid characterized as C double bond O stretching bands. The exact frequency of absorption nature of the functional group as a whole is discussed below. Acid chlorides show C double bond O and C double bond Cl stretching band. C double bond O stretching band appears in the region 1810 to 1775 cm. Conjugation with lowers the frequency of absorption to 1780 to 1760. The CCl stretching region 800 to 653 cm. Acid anhydrides. Acid anhydrides contains two carbonyl groups. Vibrational coupling between them gives rise to two C double bond O stretching bands. Asymmetric C double bond O stretching, which absorbs in the region 1830 to 1800, and symmetric C double bond O stretching, which absorbs in the region 1775 to 1740 cm. As expected, conjugation with alpha, beta, C, double bond C, or aryl groups shifts the absorption to lower frequency, while rings, stain, cyclic anhydrides move the absorption to higher frequency. Besides this, anhydrides also show multiple bands in the region 100, 1300 to 900 cm due to CO stretching vibration esters. The two most characteristic features of the IR spectra of saturated aliphatic esters are the strong C double bond O stretching absorption, which appears in the region 1750 to 1735 cm, and CO stretching absorption, which appears in the range 1300 to 1000 cm. Conjugation of C double bond O with alpha beta double bond or aryl group shifts the C double bond O stretching absorption to lower frequencies, while conjugation of the single bonded oxygen atoms of the ester with alpha beta double bond or aryl group shifts the absorption to higher frequencies. Thus, vinyl and phenyl esters absorb at higher frequencies as compared to corresponding saturated esters. In case of cyclic esters, the C double bond O vibrations are shifted to higher frequencies with decreasing ring size. For example, like acyclic esters and cyclic esters, also conjugation with the C double bond O group lowers the absorption frequency, while conjugation with the oxygen atom increases the absorption frequency. For example, ring size effect, alpha beta conjugation, conjugation with oxygen. Amides. The IR spectra of amides show the following four characteristic absorption bands. All amides show a strong C double bond O stretching band in the region 106, 10680 to 10630 cm. Free NH2 group of primary amides show 2 NH stretching bond around 3500 cm and 3400 cm. H bonded NH2 group of primary amides also show 2 bands but at little lower frequency with 3350 cm and 3180 cm. Secondary amides, on the other hand, show only one NH stretching band around 3430 cm in the free state, and in the free region 3320 to 3140 cm when H bonded tertiary amides, due to the absence of hydrogen on the N atom, however, do not show NH stretching band. The NH bending vibration of primary amides appears in the range 1640 to 1620 cm, while that of the secondary amides absorbs in the range 1590 to 1550 cm. In case of primary amides, the CO stretching band usually partially overlaps with the NH bending vibrations as shown in figure 11.27. Primary amides also show C double bond N stretching vibration around 1400 cm. Cyclic amides lactams give the expected increase in C double bond O frequency with decreasing ring size. The characteristic higher absorption frequencies of carboxylic acid derivatives are summarized in table 11.19. Look at the table 11.19 characteristic higher absorption frequencies of carboxylic acid and derivatives. Look at this another table. Amines. The infrared spectra of amines show characteristic absorption bands due to NH stretching, NH bonding, and CN stretching vibrations. Table 11.20. Look at this table 11.20 characteristic IR absorption of frequencies of amines. Primary amines show 2 NH stretching band of medium intensity in the region 3500 to 3020 200 cm. Secondary amines show only one band, while tertiary amines have no NH stretching bands. Hydrogen bonding tends to shift the NH stretching band to lower frequency, but the shift is much smaller than in case of alcohols, carboxylic acid, since the hydrogen bonding in amines is much weaker than in alcohols, carboxylic acids. Primary amines show medium to strong in plane NH bending vibration in the region 100-640 to 100-560. While secondary amines show weak bands of this type in the region 1600 to 1500 cm. Amines also show out of the plane NH bending vibration around 800 cm. Beside these NH stretching and bending vibration, all amines show medium to strong CN stretching bands in the region 1300 to 1000 cm. Aromatic amines, however, absorb at a higher frequency as compared to aliphatic amines, which absorb in the region 1250 to 1000. The reason why aromatic amines, the CN shows CN stretching absorption at higher frequencies that due to resonance, the carbon-nitrogen bond requires some double bond character. For illustration, IR spectrum of N-propyl amine in figure 11.28. Look at this figure 11.28. Amine salts such as hydrochlorides show a broad band in the region 3000 to 200. Stretching amine salts show NH bending vibration in the region 1610 to 1500. Show two bands as symmetric at 1610 cm and symmetric 1500. Nitro compounds. The IR spectra of nitro compounds show two strong absorption band in the region 1370 to 1300 cm due to asymmetric and symmetric stretching of N double bond. Or even respect nitrohexane shows strong absorption bands at 1550 cm to 1380 cm. Conjugation aromatic ring shifts these bands to lower frequencies. For example, nitrobenzene absorb 1350 cm. Nitriles. The infrared spectra of nitriles show a sharp band of medium intensity in the region C triple bond and stretching vibration. Conjugation with double bond or aromatic ring moves the frequency. Spectroscopy. The IR spectrum of a compound provides much more information than a UV spectrum. Then at almost all the functional groups shows characteristic absorptions with the definition. Important applications of IR spectroscopy are given below. The determination of molecular structure by IR spectroscopy is very helpful in determining of unknown organic compounds. By an inspection of the positions of absorption band, it is possible to identify the functional groups present in an organic compound. For spectra exhibits a strong band at 100 1715, the compound almost saturational group, but this alone, however, does not reveal whether the functional groups present is an acid, an ester, or an amide. This information, coupled with the presence of other bands, help us in determining the nature of functional groups present in an organic. Spectroscopy help us in the identification of functional groups present in an unknown, but it cannot always replace chemical and solubility tests used for identification of functional regard. Or negative evidence is considered much more conclusive than the positive evidence. The IR spectrum of an unknown organic compound does not contain absorption typical group. The molecule does not contain the functional group. Studying the progress of reaction. Progress of many organic reactions can be followed readily by examining the IR spectra of liquids. Small amounts of mixtures withdrawn from time to time. For example, we can study the rate of oxidation of a secondary alcohol to a ketone, the rate of disappearance of the OH stretching vibration around 3400 to 3200. Due to reactant or the rate of appearance of the C double bond O stretching vibration around 1715 cm. Due to the formation of the product determines the rate of the reaction. Similarly, the progress of chromatographic separations can be monitored by scanning the IR spectra of some selected fractions. Identity of two compounds. IR spectroscopy is often used to establish the identity of two samples for details referred to. Detection of impurities. IR spectroscopy can be used to determine whether the given compound is not pure or not by comparison of its IR spectrum with that of the pure compound. In general, the spectrum of a pure compound will have fairly sharp and well resolved absorption bands. In contrast, the spectrum of an impure compound not only contains extra bands due to impurities, but the spectrum on the whole will have broad and poorly resolved absorption bands.